Alright, we're going to call this one part 2 of the lesson on Cartesian equations of planes in R3. So we're just going to run through some examples. So very straightforward example, determine the scalar equation. So scalar equation looks like this. In R3, so that's the scalar equation of a plane with the normal vector 1, 2, 3 passing through the point -3, -2, -1. Okay, we know that this ABC is the normal vector. So A is 1, so I can just write x, B is 2, C is 3, and I don't know D. So now I need to get D. How do I get D? Just sub that point in. X, -3, Y, -2, 3, -1, or Z, -1, plus D equals 0. Now just solve for D. -3, -4, -6, plus D equals 0. So that's -10 plus D equals 0. Therefore, D equals 0. Therefore, the equation is what was it? X plus 2y plus 3z plus D, but D is 0. Or sorry, 10 plus 10 is equal to 0. So that's your scalar or Cartesian equation of the plane. Okay, example 2, or if you prefer, the second example. So we want to find the scalar or Cartesian equation of a plane containing these 3 points. So first thing we need is, well, ultimately what we need is the normal vector. But we don't have the normal vector, we have 3 points on the plane. So how are we going to find the normal vector? Well, here's a suggestion. Can we find a direction vector or a vector on the plane? Sure, AB, right? If A and B are on the plane, then the vector AB is the direction vector of the plane. So M1 will be, subtract B's from A's, so -3, -1, 2. And then if I want another one, M2, whatever I want. Which one should we do? Let's do BC. Could do AC. So I'm going to do BC. So my C's minus my B's. Right, since B and C are on the plane, the vector BC is a direction vector. So 2 minus -2, 4, 3, -4. So here are 2 direction vectors for this plane. So how do we get the normal vector? Well, the normal vector, or a normal vector, is just the cross product. Right? Cross product is a vector perpendicular to the plane. So all I need to do is cross these 2 vectors. Cross 4, 3, -4. So cross product, just use the cross product formula. You know what? I'm going to just write down the answer, and the answer is 245. You can confirm that by doing the calculations here. So magic happens, use the formula, and then we get to there. Skipped a couple steps, you need to fill those in on your own. Okay, so now AX plus BY plus CZ plus D is equal to 0. So I know A is 2. I know B is 4. I know C is 5. And I don't know D. So how do I get D? I just need to plug in a point. So any one of these 3 points. I'm going to take my favorite point, 1, 2, 3. So 2 times 1 plus 4 times 2 plus 5 times 3 plus D is equal to 0. 2 plus 8 plus 15 plus D equals 0. D is equal to 25. Therefore, the equation is what was it? 2x plus 4y plus 5z minus 25 equals 0. There is our equation. Okay, next one. Okay, final example. We want to find the angle between two planes. So plane 1 and plane 2. So if you remember, we did this in R2 for lines. We figured the angle between two lines, and all we did was we found the normal vectors of both, so that's easy. It's in Cartesian form. 2, 4, 5, and then the second normal would be 1, 2, 3. And if I want to find the angle between them, that's just equal to the angle between the normals. So I'll use the angle formula, cos inverse of n1 dot n2 over magnitude n1 magnitude n2. So cos inverse of n1 dot n2, so 2 plus 8 plus 15 all over the square root of 2 squared is 4, 16, 20, 45, and the square root of 1, 9, 14. So that's cos inverse of 25 all over root 45 root 14. So theta is equal to, get out your trusty calculator. Okay, I got 5 degrees. Okay, so that's the acute angle, or if you got the obtuse angle, right, there's always 2, you get 175 degrees. So that's also a possibility. One quick comment about this type of question. Remember in R2, we could do this for vector equations, right? If we had a vector equation, this T1, 3, and then, so this was R1 and R2. Then if we wanted to figure out the angle between them, we just figured out the angle between the two direction vectors, and that's fine, it worked good in R2. But what about, good, it worked good in R2. But what about in R3? We did it for Cartesian, when we looked at the normals, but what about if we were given it's the same thing. So I'm given two equations. So that's S1, this is S2. Okay, so I'm given 2, and I want to find the angle between these. What is angle? I'm not going to do this one, but I'll just talk about it. Well, in R2, when we were just looking at lines, we just looked at the two direction vectors, found the angle. The problem here is this line has two direction vectors, as it does this. So do I find the angle between these two, or these two, or these two, or like, what do I do? There's too many direction vectors. And the answer is none of them will work. You can't do it for any of them. You must find the normal vectors, and then find the angle between the normal vectors, the way we just did in that previous example. So Cartesian equation of a plane, a little better for this, right? You can't do it with the vector equations, because there's too many direction vectors.